Let's show. Okay, so we discussed about the electrostatics and magnetostatics so far now. Also have written a co-exam on it. So therefore, you should be familiar with that, I believe. So now we are actually moving to next topic, that is the time varying electromagnetic fields. So this time varying electromagnetic fields, actually they will be completely different from the static fields. It won't be repeating like the electrostatic fields. So in fact, if you see the electrostatic fields, uh, the electric and magnetic fields, they themselves complement to each other. And similarly, the time varying magnetic field also completely complement to both the static, electric, and magnetic field components. So in this class, we are going to discuss about this Faraday's law, and Lenz's law. Obviously, it will come along with Faraday law itself. The next class, we are going to see about the displacement current. Then we will directly go to Maxwell's equations just after that. So today we will discuss up to this. Tomorrow we will discuss. And this time varying magnetic field is a very small module. You can easily finish it just in 3 classes. We started with Coulomb's law, then we move to Gauss law, and these two laws are going to state about the electrostatic field and how this fields they how these electrostatic field induce force upon a particular charge, and similarly if a force is if the particular field is exerted by a uh, bunch of charges, and what is the relationship between them. So this is what we have discussed in the Coulomb's law and Gauss law. And very similar manner, we have two other laws for magnetostatics, the Biot-Savart law. So, and then we have Ampere's law. So these two laws going to tell the same phenomena, that a time varying current going to produce magnetic field. And similarly, the magnetic field is going to produce the current. So that is what actually hmm, both these laws actually going to describe the uh, magnetic magnetostatics. Okay. And these all things can be summarized like this: Coulomb's law, Gauss law, and then the other two important equations to solve the electrostatic problems for boundary conditions, that is Poisson and Laplace equations will come. Then magnetostatics. So all these things are actually summarized here. Now we are actually moving towards the time varying fields. So in case of time varying fields, they will be having another name called electro electrodynamics or magnetodynamics, like that. And in case of the electrodynamics, we have about three important people. One is Michael Faraday, and Joseph Henry, and of course the Maxwell himself. So these three people actually they have described all these phenomena, and particularly Michael Faraday and Joseph Henry, actually they were actually in two different places without knowing each other. They independently developed some of the very important nature of the time varying fields. And what is that? So a time varying magnetic field would produce the electric current, but the magnetostatic field does not. So what is the meaning of that? If there is a, let's say there is a loop, and we are having magnetic field, just it is passing by, and this magnetic field, whichever is calculated uh, over the closed surface, whatever it is here, and so this, if it is a non-varying with respect to time, then it is not going to produce any electric current. And so which means, let's say you are keeping a bar magnet in the center of the wire, and even though the magnetic field is keep on produced by, it is not going to create any uh, so-called electric current. So this actually both the people experimentally proved themselves. but their motivation is completely opposite. One, Michael Faraday started to work towards the generator, and Henry started to work with respect to transformers. So they are actually completely orthogonal to each other. So, by the way, but anyhow, Henry, uh, uh, he worked towards the transformer, and he named after this the unit for inductor, and hence most of the people phrased this law as Faraday's law. Of course, Maxwell would have given the name for it. So Michael Faraday, uh, he actually almost this was his final work. I hope so. So he took a bunch of wires. So it is like you just go for just a bunch of wires just around that, and you can extend the wires into two. And we are going to calculate we are going to keep some ammeter here. Okay. And whenever we keep a bar magnet just like that, and it is going to produce the magnetic field. Okay. So, but this magnetic field is always be constant. It is not a time varying one. So obviously this didn't created any current at all. But the moment he started to move uh, towards it, and when we go outward direction, so there will be a current produced, and the current produced is exactly opposite to the Biot-Savart law, how it is. So Biot-Savart law states that if there is a current carrying conductor and it produces the magnetic field at a distant point, which will be perpendicular to both R vector and the current. So let's say if you use the so-called right-hand rule, then the magnetic field will be just in this way. But in case of the magnetic field and the current, whatever it is produced, they will be opposite to each other. And this is actually first realized by Lenz. So that is why this is defined as Lenz law. So the Lenz law states that the the magnetic field, the time varying magnetic field, which means that which is in the motion. Okay, the source of the magnetic field is in motion or the wire is motion, both. So if this is the position A and this is the position B, and there is a change in these two positions, or both can be changed parallelly, or anyone can change. And by the way, the magnetic field become time varying, and this magnetic field will induce the current. So that induced current will create a voltage across the uh, terminal, and that is what we call induced EMF. And this same thing is also referred as this electromotive force. So due to the movement of the source of the magnetic field, in other words, when it is moving or in motion, which we call the motive force, the whenever there is a movement in the magnetic field or the closed wire, actually the loop, whenever there is a movement, and due to this movement there is a current produced, and this create a potential difference between the two terminals of the loop. That is what we call as the induced EMF, or which generally calculated in volts, which is nothing but the integral version of the current which is produced over the wire because of the induced electric field itself. So this is what the very first description about this, the time varying magnetic field, or the time dependent magnetic field, and how it interact with the closed loop. And this is actually very well written by Faraday himself in his notebook. And as of course Maxwell was, sorry, yeah, Faraday was not a great mathematician. He left it to many mathematicians, including people like Lorentz, and then Maxwell himself, and Oliver Heaviside. Like these people actually they developed the theories later, and they named it after him as Faraday's law. So this Faraday's law going to simply tell that the magnetic, the induced potential, induced electromotive force, which is VEMF, is equal to the time varying magnetic field, or the time varying the magnetic linkage. So this actually calculated by N into psi m, where psi m is nothing but the magnetic field, magnetic flux itself. So this magnetic flux, obviously, we will calculate with respect to area. So you can easily imagine this whenever the area increases, obviously the induced EMF also will increase. That is why if you see that to increase the generator power, they go for big size of generators, or they will increase the number of turns. So either way, we can increase the induced electromotive force by the loop itself. And along with the Lenz law, this negative term will come. So this indicate that the flux, whatever the flux is from the source, which is always be opposed by the linkage which is created by the loop itself. So it can be easily understood that, let's say, because of the time varying magnetic field, there is a current produced, and this current can produce a magnetic field. This magnetic field is nothing but induced magnetic field because of the induced current, and that magnetic field will be exactly opposite to the source itself. By the way, they are opposite in nature. So this is what described as Lenz law, and this is when the magnetic field is coming towards that. Let's say that the magnetic field is going away from that, then the current will be again once again opposite. So that is why this Lenz law also being introduced in the Faraday's law. So this is the total amount of electromotive force induced uh, by the closed loop, and this can be described in a very conventional circuit itself. Let's say you just have a closed loop of a particular circuit. The circuit has a load, some resistor is available, and there is a battery, and this battery is connected with the wire, and the other end of the resistor is connected with the other end of the battery. Therefore, this exactly closes. And we very well know that the potential due to the battery and will be exactly equal to the potential due to with respect to the resistor, but it will be in opposite direction. That is why the total potential throughout the circuit will be zero all the time. Therefore, we can say that the battery which produces the so-called the electric flux to move the point charges, that is the electrons, and which we often refer as this field due to the charge. So this field due to the charge which closes itself, and there comes the closed path integration always be 0. So this is the very natural, we can call it as a Kirchhoff's law itself. But what about the the electromotive force which is created? The electromotive force is exactly perpendicular to uh, the electric field which is induced by the electrons, and this is not going to flow through this circuit. Rather, it will be staying within the battery itself. Since it is staying within the battery, this is not going to have any closed loop or anything else. Therefore, this value will become always be equal with respect to the voltage drop across itself. So which we call as VEMF. And this VEMF and this, just if you multiply with the so just if you divide by this R, you will get the current. By the way, the induced EMF is nothing but the integral version of the electromotive force inside the battery with respect to the loop itself. And this closed loop always will be having I into R, and that is what we often refer as Ohm's law itself. So this description have been written so long ago, but originally described within the concept of Faraday law itself. So this is what the Faraday's law. So I will summarize what is Faraday's law itself. So whenever you have a loop and when there is a current flow takes place, so we all always know that. So when there is, let's say there is a loop, closed loop, and there is a current flowing through that. And because of this flow of current at a particular point, we can see that there is a magnetic field will be generated. And this magnetic field, of course, it corresponds to a magnetic flux itself. So a current carrying conductor will produce the magnetic field. Yes, completely static magnetic field it can produce. But on the opposite side, whenever there is a static magnetic field is crossing the closed loop, it won't produce a current. So this is what the just opposite one. So what to do? Why it is not so? Because in a particular source, always this magnetic field, the overall magnetic field in a closed path always be zero. Therefore, there is no current cannon. But in case of time varying one, since the time dependency is coming within the instantaneous time, this magnetic field is not closed. So obviously, you will get the current itself. So that is what we are calling as the Faraday's law. So you have to understand this not vice versa concept. Yet, yes, current can produce the static magnetic field, but a static magnetic field cannot produce the electric current. Okay, so that is what you have to understand out of the Faraday's law. Now, this Faraday's law we can easily substitute with the both the conditions with respect to electric field and magnetic field, and this way we can easily relate the electric and magnetic field of with respect to the time domain. So this we already have seen that the total flux which is varying with respect to time, this corresponds to the potential induced, that is the induced EMF itself, which is nothing but the integration of the electric force with respect to the loop itself. So if there is a closed loop and there will be a induced EMF, and this induced EMF is when we integrate over the closed path, we will get the total potential. And similar way, if you, this is actually, we are going to substitute for the left hand side. And for the right hand side, we have time varying magnetic field, the differential version of the time varying magnetic field. So which can be stated as the time varying, and this psi, we know that the psi is nothing but integration of B over the closed surface. Sorry, it is an open surface. There is no closed something like that. So within this area, whatever the magnetic field is captured, that can be integrated over the surface. And the time dependent is still coming here. And now we are going to compare this left hand side and right hand side, then you will get this equation. So this which directly gives the relationship between the electric field and the magnetic field. And this is one of the very important expression in the field of electrodynamics. With this equation, you can solve many important problems. So the induced EMF is nothing but the closed path integration of the induced electric field due to the means with respect to the loop itself. And with respect to the loop, there is a area is created, and this area is going to capture the time varying magnetic field, and that produce the magnetostat means this the electromotive force itself. So both the way we can link it. Now, this electromotive force can be produced by multiple means. Since the motion is very important one here. So as I already said that if there is a, let's say there is a South Pole, North Pole, and the magnetic field is created. Okay. And so, and this is position A, and this is position B. Now, if you move this magnet up and down, then for one time you are actually keep on going towards it and you are going outward direction. In this way, you are actually changing the B with respect to time. So here the magnet is moving, but the so-called the loop is stationary. On the opposite side, the loop can move and the magnetic field will be stationary. The loop can move towards it or outward direction, or it can rotate any means. So finally, it has to cut the magnetic flux, and thereby we can get the so-called unclosed magnetic field, which is going to produce the current. So there are about three possible way we can get. One is there is a stationary loop and there is a time varying magnetic field. So by this way, we can get this the magnetic linkage can be done with between the two loops, and we can get the current control and what we call actually as a transformer EMF, which is nothing but, so due to the there is a AC source, and this AC source is going to produce the time varying current. This time varying current will produce time varying magnetic field, and this time varying magnetic field is going to create a current here. And so this also time varying one itself because this value, whenever it is keep on changing, then obviously this is also so. So if so, by the way, you can have a control over the current what is going as a input and output, and this transforming uh, magnetic field, which later give the word the transformer. So this originally developed by uh, Henry himself. And the second idea is nothing but the time varying loop. The loop can vary with respect to time, the loop's position or the so-called the orientation with respect to axial manner it can rotate. And there we can keep the stationary magnetic field. And that is what the idea behind the motor and generator. And we can have both the loop also time varying one and the magnetic field also time varying one. And this is nothing but combination of both transformer and motor. Now, very recently, this kind of idea is coming up to make the multiple motors yeah, induced by. So, and we can also make the sections of the magnetic field. So you could have seen this type of the magnets. They are actually kept in the four directions, and the loops are inside that. And the center there will be a rotor. So combination of both idea, and this system is little complicated, while these two are very simple systems. Now we will explore this two, the first two systems, and we will see some numerical problems out of that. Case one, the field is actually time varying one, and the loop is stationary. So we can have the Faraday law itself. The Faraday law, we already have seen that it is nothing but the integral of the electric field with respect to the loop, which is equal to the overall magnetic field captured by the loop, and which is a time varying one. So both going to produce the electromotive force. And this electromotive force, now we can expand. So you can see that there is a, surface, a surface integration is there. So in this side also, if you get the surface integration, then we can cancel the integration, then we can easily get the differential version. So how to do that? So we know the Stokes theorem. Stokes theorem always says that if there is a closed path integration, then you can make it as a surface integration. Just you have to take the vector and you have to take the cross product with the del operator. That's all. So this del operator is introduced here, and this line integration becomes the surface integration. You should always remember that the closed path integration become open area integration. Now both are open area integration, and thereby we can easily cancel out. And we are going to assume that this is completely uniform medium everywhere. So by the way, we can easily cancel out this integration and we will get this equation. So this is one of the very, very important equation. We can see that directly this time varying magnetic field will produce the electric field, and in opposite that the electric field can produce the magnetic field. So both are actually highly linked. This is in fact very true when there is a, let's say there is a electric time varying electric field is available, and obviously it will produce the corresponding magnetic field with some 90-degree phase difference will produce. So that is what we call as a uh, the field exchange the just a minute. Yeah. So this time varying field can directly give. So since this magnetic field is not equal to zero, anyway, this is not equal to zero. If it is not equal to zero, then its differential version also will not be equal to zero. And if the differential version is not equal to zero, we will always get del cross E is not equal to zero. And this is true for time varying. For time varying magnetic field, it is true. But if it is a stationary one, then this vector will become zero, and this means that such a electric field will not be induced at all, and therefore current also will not be induced. So this is what the relationship between this two. So, and this same thing when you see in the electrostatic, this completely equal to zero. So that is what the difference we can stay directly we can find in the Maxwell's equation itself. So this is the case one. And in case of case two, the loop is moving and the field is static. So what for this, what we are going to do? We are going to take two bar magnets and we are going to put this polarities exactly opposite to each other and such a way that this magnetic field is exactly uniform throughout the region. So we got the magnetic field and this integration will give the psi. Okay, so this and this is not time dependent. It is a time independent one. So beta b is going to be constant, but rather we are going to move the uh, this loop. So this loop, whatever it is you are seeing here, it is going to move. Let's say it is going to move along this axis. So when it is moving, then it will get a velocity, and that is defined as a u vector. And this u vector directly can produce the force. So this is the force due to the magnetic field, and with respect to um, the moving charge or the moving loop itself. So it is moving in a particular fashion. As I already say that it can move in a zigzag manner, vertical manner, in a circular manner, any manner it can rotate. But ultimately it has to cut the flux, the magnetic flux. That is what it's supposed to do. And now we got this expression. Now you just bring this q in this denominator, then you will get the the induced electric field due to the uh, B itself you can get. So this is directly the uh, the induced electric field, and this induced electric field will be just flow just around it. Okay, so this is the electric field induced. And this induced electric field, if you integrate over the closed loop, then you will get the total uh, flux, sorry, the total electromotive force which comes across this will come. This potential difference we can find. So that is what we can get out of the Faraday's law itself. And if it is a proper rectangle, then only this line and this line is going to get it. So the current will be flowing in this direction and this direction. So both are going to make the loop correct. So just you are going to add each other. And by the way, you will get the total induced EMF is nothing but simply the velocity into B into L. This is true for a simple rectangle loop which is having a length L, which is having a length L. And so if it is a circular one, if it is having different shape, you will get different. So that is what the moving loop has. And both when you put together the moving loop as well as the time varying one, just you have to superimpose both the concepts each other. Then you will get the induced electric field due to the time varying magnetic field as well as the moment of the loop. Both are going to induce the total. So by this way you will get very high current produced. So this is actually a very interesting idea, and this can give this very advanced transformer concepts or advanced generator concepts. It can be developed, but doing both together mechanically is very difficult job. This is what the Faraday's law, and out of Faraday's law, we got three important circuits, which is actually we can say that this Faraday's law we can say it is very important one for electrical students because this transformer and motors and generators is life for them. Let's take a very simple example and how to solve the problems of the Faraday's law. So what we have here is there is a loop and this loop ended with a load of resistance R, which is about 0.1 ohm. And this loop is having four nodes A, B, C, D. And this is actually kept about phi equal to 90 degree with respect to the x-axis. Okay, so this is the initial position of the loop, and now we are actually allowing yeah, uh, a constant magnetic field, and this magnetic field is actually running along the x-axis. So there is no time dependencies here. So there is a uniform as well as static magnetic field. And this loop actually going to rotate along the phi direction with a velocity of with a frequency of 50 hertz. So this clearly says that this d by dt, which is nothing but omega, which is nothing but 2 pi f, where phi is 50 hertz. So obviously you will get 50 into 2 pi, which is nothing but 100 pi. So this is the angular velocity of the loop. This loop is actually going to cut this magnetic field, and hence it will produce the induced EMF. This induced EMF going to produce the current, and that current will flow through this resistor, and thereby we will get the induced EMF in terms of the potential EMF, which is nothing but the induced current into the resistance. That's all. So that is what the problem is. Now the question is, like, at time t equal to 0, this is the position, and at time t equal to 1 millisecond, let's say it is somewhere else here or somewhere else. Okay, this is, let's say, time t equal to 1 millisecond, and at this time it is actually under movement, and at this, because of the movement, then what about the total EMF produced, and what about the current induced because of that? That is what we are going to find. Now once we calculated, then we can easily calculate if it is moving around, whenever it is moving around with respect to the frequency of 50 hertz, then obviously within about within about 100 millisecond itself, it will close the loop. So therefore, we can find the total current induced because of the one full cycle. We can easily calculate out of that. So that is what the overall objective. Let's see how to do that. Okay, so we know about this the Faraday's law. So Faraday's law tells that the induced magnetic field is equal to the cross product of the velocity vector and the magnetic field and the dot product with the loop itself, and you are going to do the closed loop integration. So for this you should know what is u, what is b, and what is this dl. You should remember all of them are vectors. Okay. So here we are going to define this dl. Dl is nothing but the loop which is actually carrying the current, and in this the question is asked with respect to the side DC. So the D is here and C is here, and this is just perpendicular direction along the Z axis. Therefore, you can say that the small dl vector, so this dl vector can be nothing but dz vector into az vector. It is very, very simple. So we got the dl vector, and b vector, it is already known. So b is nothing but b naught a z vector, sorry, ax vector along the x direction. Now we need u vector. So u vector is nothing but the angular velocity. So the angular velocity is nothing but this particular line, which is actually moving along this direction. So which is nothing but at a distance of rho. So this is, let's say, this is nothing but rho, and this particular point is moving along the phi axis with respect to time. So we can easily say that rho d phi by dt into a phi vector. So rho is known, and this d phi by dt is nothing but the angular velocity itself, that is omega. And omega we can easily expand as 2 pi f. F is 50 hertz, which is already given. Therefore, omega is nothing but 100 pi. So as of now, we haven't substituted any value. Just let us go with that. Now you can see that the moment, because this vector is along with respect to cylindrical axis, cylindrical, and this also with respect to cylindrical, and but this one is with respect to XYZ axis. So we have to convert that to cylindrical coordinate system. So first we are actually converting this to cylindrical coordinate system. So this is a rectangular coordinate system. This is cylindrical coordinate system. And now we have to take the cross product with U and B. So when you substitute this A, B, C, and you are going to substitute for this U and B, both you have substituted. So very simple idea is whenever you have Z axis or any particular axis with two zeros, then obviously this particular axis alone will exist. This is a very simple rule. So that is why you have to calculate only for Z axis alone. So with respect to Z axis, you will multiply this and this. So for this is plus, for this is minus. So anyway, 0 into this value become 0 itself. So you will get minus of rho omega beta naught cos phi. So that is what it is given here. So we got the cross product of U and B. Now we have to take the dot product with the DL. So DL, we know that it is already AZ vector is available. Here also AZ vector. Then when you multiply this, you will easily understand that you will get minus rho omega beta dz cos phi, like that way is going to come. Yeah, we got here. So we are going to take the dot product. This dot product will simply will give dz itself. And we are going to substitute all the value. You got this vector, just you have to integrate. So we are going to integrate for this 0 to 3 centimeter. And the 3 centimeter now converted in terms of meter. Why it is converted in terms of meter? Because this beta, this B is given in terms of meter, that is why. So when you substitute this, you will get everything. Just you have to integrate. When you integrate over Z, you will get the 0 to this value and to the first value and the second value. Just you are going to find the difference and you will get it. And now we got this, and now we have to get the this induced EMF with respect to time. So how to get with respect to time? So what we know is the angular velocity omega is nothing but d phi by dt. Therefore, phi we can easily calculate as, just you have to take integration. When you take integration, you will get omega t, and this omega t plus some constant will come. How to calculate the constant? For that, we have to apply the initial conditions. So the initial condition is at t equal to 0. We got phi equal to pi by 2, because that is the initial position of the loop. So just then when you substitute this here, you will get C naught. C naught will become pi by 2. So just you are going to substitute here. Now we got the expression for phi in terms of time t. Just this has to be substituted here. Then you will get this expression. We got the induced EMF with respect to time we got. Hereafter, we have to just work with respect to time. So at any instantaneous time, we can calculate the induced EMF. So we are going to substitute t equal to 1 millisecond. So when you substitute t equal to 1 millisecond, just you are going to substitute this 1 millisecond, and by the way, you will get this sign. So it is, you can easily understand that this is the P EMF. At time t equal to 0, there is no EMF, but as time progress, it is going to reach a high value. Then it is going to get the low value because the loop is going to take the other side. So I hope you can easily understand that. So this is the magnetic field. So the loop is this way, it is available now. And when it is going for 90 degree, the loop will be here, and it is just along the direction of B. Obviously, there is no magnetic field capture. Then when it is this side, still the magnetic field is in this direction, but the flow will be in the opposite direction. So you will get negative sign. Then when the loop is closing about 360 degree, once again, it is along the direction of the magnetic field. So there is no induced EMF. So by this way, you will get sinusoidal description, sinusoidal behavior will come for induced EMF for this loop. And this is only for this And what about this? And with respect to velocity, this is going to be constant only. So there won't be any effect because of this particular loop. So you got the induced EMF. So how to calculate the current, what is passing through? Already we know that there is a resistance of 0.1 ohm. Then we can calculate the induced current, which people write as induced E, which is nothing but V EMF divided by resistance. You can calculate the current. So you can do for 1 millisecond, 3 millisecond, whatever the time you like. Okay. So within that you can get it. It's a simple workout. And you have one more method. It is given in this book itself, and the answer is also available. Kindly work on that. So if you have any questions, you can ask.